To have a criteria, a systematic way to measure the difference between the model prediction and the over expectation, um, we need a method called loss function. We formulate everything into a succinct, precise number, one number, and we call this the loss and want to minimize the loss by comparing the model output and the target. In this case, I'd use a loss function called dot negative log likelihood loss. That is to measure the difference between the model's prediction of the logarithm of the probability of each class, which is very mouthful to talk, and the real class labels. So in the notebook is put your cursor between the parentheses and hit Shift plus table, the table key on your keyboard, and it will show the argument and this function expected. Let's have a check. H is our model's prediction, and remember that above, when we get the data, we have a pair. One is the observation of the pixels and the other class label y. So this is our desirable y. Okay. We can also do a sanity check, such as, look, in this edge we have the second, the 1, 2, 3, the element 2 to have this value, and we want to increase this value to improve the probability, the prediction of the model on the first level. Have a look at this. If I do another, I have another copy of H. I think I need H clone or something. But let's for simplicity's sake just do this computation. Increase the corresponding value a little bit and recalculate the loss to see if this will improve the loss. Of course, in this way we are cheating, because you need to improve the model so that the model prediction approaching the desired value, while you should not directly adjust the prediction itself, right? But let's just have a look at the idea of assessing the prediction using a loss function. Look, this is minus 3.73 and this is minus 3.42, and this number is smaller than this one, and the loss gets lower, and I wouldn't say the model gets improved, but I see the cheated prediction gets improved. The natural next step is to arrange such a method to improve the model parameters, which is called optimization. And Torch also provides us a set of optimizer. Let's from this import. There is a collection of optimizers for you to choose. I use this one, which is pretty standard and popular. Okay, let's run this, and let's see. We have optimizer. Instantiate such optimizer class, and for optimizer to work, the most important thing is to tell the class to create such object to adjust this set of parameters. And the set of parameters in our case is the DNS parameters. We have encountered this method previously. In that case, we just want to list the parameters of one of DNS components. And this part is the motivation behind our practice of organizing all the components of a neural network together so that we can put all the parameters together and give it to an optimizer for training the model. And also it needs a parameter called learning rate. Well, that is a little bit difficult to explain, which means because in training optimization, you calculate a promising direction following which you adjust the parameters, but that direction is promising only locally. At the point where you are searching at this very small local area, that direction would be good. But if you step too far, you may hit some wall or something unexpected. There, in this way, in this respect, we add a parameter called learning rate to limit our step each of the iteration. Normally, we set it up as a small number. So yes, and this is the optimizer. Let us create this optimizer, and let's put everything together, or a little bit together. So now we have the DNAT. Okay, opt dot. This is to clear everything we have already calculated about the promising direction along which to adjust the parameters, and then we would use the DNAT to predict on the set of data, and then we will compute the loss f dot and error loss h and y. So this is the loss, and then the next step is very important, and that is a very great facility provided by the modern computational frameworks. It saves you mountains of time. It can automatically calculate the promising direction along which to adjust parameters. The calculation of direction is very tedious and time consuming, but now you can use only one statement to perform that. It's called backward. You may have heard the famous backpropagation algorithm, and this backward method performs backpropagation to calculate the direction. And now, having the direction calculated, you can let the optimizer to have a step to actually adjust the parameter of DNAT a little bit. So that would be the idea. Maybe you can also print the loss to have a look at its progress. Let's try. This actually gets a little bit larger, but look, sorry, this loss. This looks like working, but actually it is not. We will stop here for this very initial tutorial. I will provide the correct version of the model, the trainer, and the optimizer in the notebook. There's very slight difference between the actual working model and the one we have just introduced here. Please try to find out the difference and study a little bit for yourself. And so to summarize, in this tutorial, we see in under 1 hour, hopefully, we see the process of getting familiarized with the environment, have a look at the tools we use to manipulate the numbers, and load data as the load image data as the numbers that we can manage and build data models and in the framework of deep neural networks, and apply the computational tool apply the tools provided by the computational framework to optimize our model so it can perform the task of interest. So welcome to our course, and we will discuss a lot of aspects in this subject in our semester. Have a good weekend.